Chapter 11, Work and Energy. Work. We do different types of work in our day-to-day life. For instance, singing, playing, reading, climbing, talking, cycling, and many more. To perform all these activities, we require energy. This energy is obtained from the food we eat. Animals are also involved into various activities. For instance, to find food, to jump, to run away from their enemies, or to find a safe place to live in. Animals are used to lift weights, carry loads, or pull carts. All such activities require energy. The fodder eaten by the animals give them energy to carry out these activities. Also, various machines that we use in our day-to-day life like automobiles, fans, water pumps, etc. perform some kind of work. Have you ever wondered from where do they get energy? Well, they get energy from electric current and fuels like petrol and diesel. Thus, energy is required to carry out work. Work is closely related to energy and power. Let us learn more about work and energy and find relationship between them.
Scientific concept of work. We use the word work in our daily life in a very general way. Like a person is working in a bank, or students do their homework regularly. From morning till you go to bed, you do different types of works like brushing your teeth, watering plants, helping your mother in kitchen work, going to the market to fetch vegetables, ironing the clothes, and many more. Ordinarily, the word work means any mental or physical activity. However, in scientific terms, the word work has very different and specific meaning. Look at the following examples. Kausar is doing her homework, completes all her assignments given in school. Bullock pulling a bullock cart. Iqbal stands all day holding 10 kg weight on his shoulder. Samir is a computer operator and spends his day operating the computer. Coolie carries the weight from rickshaw stand to the train. John walks for a distance of 5 kilometers for his morning walk. From the above examples, who are doing work in scientific sense? In scientific terms, Kausar, Iqbal, Samir have not performed work, in spite of working hard. Whereas Bullock, Coolie, and John are said to be doing work. In scientific terms, work is a physical quantity and said to be done when a force applied on a body brings out a displacement of the body. To understand the scientific definition of work, let us consider a few more examples. 1. A girl pushes a trolley. The trolley moves through a distance. The girl has exerted force on the trolley and it is displaced. Therefore, work is done. 2. A boy is lifting a book through a height by applying some amount of force. The book is displaced through a distance. The boy has exerted a force and the book is displaced. Hence, work is done. Now, can you tell the two conditions need to be satisfied for work to be done? These are: 1. A force should act on an object, and second, the object must be displaced. If any of the condition is not observed, then we say the work is not done in scientific term. Now you can observe in the case of Kausar and Samir that there was no force and displacement of an object, while in case of Iqbal there is force acting on the weight, but there is no displacement of it. Hence, there is no work done by the force. Work done by a constant force. Now we are in position to define work in physics. Work is said to be done by a force when the force is applied on the body displaces the body. Now let us find the work done by a constant force. Let us consider a constant force, F, acting on an object. Let the object get displaced through a distance in the direction of the force. Let W be the work done. The work done by the force is defined to be equal to the product of the force and the displacement in the direction of the force. Therefore, work done is equal to force into displacement. W is equal to F into S. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Did you know? The quantities force and displacements require direction as well as magnitude for their complete description. Work has only magnitude and no direction. Hence, work is a scalar quantity. Units of work. The SI unit of force is Newton, N, and that of displacement is meter, M. Hence, SI unit of work is Newton meter or joule. If a force of 1 Newton displaces the object through a displacement of 1 meter, then the work done is given by W is equal to F into S. 1 joule is equal to 1 Newton into 1 meter, or 1 joule is equal to 1 Newton meter. Hence, 1 joule is defined as the amount of work done when a force of 1 Newton acting on an object displaces it through a distance of 1 meter along the direction of the force. In CGS system, the unit of force is dyne, and that of displacement is centimeter, cm. Hence, CGS unit of work is dyne centimeter or erg. W equals to F into S. Therefore, 1 erg is equal to 1 dyne into 1 centimeter. Hence, 1 erg is defined as the amount of work done when a force of 1 dyne acting on an object displaces it through a distance of 1 centimeter along the direction of force. The CGS unit of work erg is small compared to the SI unit joule. Let us find the relation between them. Relation between SI and CGS unit of work. We know 1 N is equal to 10 raised to 5 dyne and 1 meter is equal to 10 raised to 2 centimeters. We have 1 joule is equal to 1 Newton into 1 meter is equal to 10 raised to 5 dyne into 10 raised to 2 centimeters is equal to 10 raised to 7 dyne centimeters. From the definition of erg, we have 1 erg equals to 1 dyne centimeter. Hence, 1 joule is equal to 10 raised to 7 erg. The work done by a force can be positive, negative, and sometimes zero. Even though there is a force acting on an object and there is a displacement of the object.
Let us understand about it in detail.
Positive, negative, and zero work. Positive work. Let's consider 2 examples from everyday life. One day while going to school, the school bus failed. Children got down to push the bus. They applied force. The bus gets displaced. Displacement is in the direction of force. Bullocks are pulling a cart. Bullocks exert a force on the cart. The cart is displaced. Displacement is in the direction of the force. In both these cases, the force is utilized to undergo the displacement. Here, the displacement is in the direction of force. Here work is done by the force and is positive. Hence, the work done by a force is said to be positive when the displacement is in the direction of the force. Negative work. Suppose you throw a ball in an upward direction. Gravitational force acting on the ball is in the downward direction. The displacement of the ball is in upward direction. Here, the displacement is in the direction opposite to the force. Here, work is done against the gravitational force. Hence, the work done by the force is said to be negative because of the displacement is in the opposite direction of the gravitational force. Zero work. Sometimes force is present, but there is no displacement produced in the direction of the force, then the work done by the force is said to be zero. Consider these examples. Amir tries to push the wall. He applies force on the wall. There is no displacement of the wall. The work done by the applied force on the wall is zero, as the applied force does not produce any displacement of the wall. A simple pendulum in the state of rest at equilibrium position is under the action of two equal and opposite forces, one weight acting downwards and the other tension in the string acting upwards. In this case, no work is done by any force since there is no displacement. Another case when work done is considered to be zero. When the applied force and the displacement are perpendicular to each other, then work done is said to be zero. When Earth is revolving around the Sun, the gravitational force of the Sun is acting towards the center. The displacement of the Earth is in the direction perpendicular to the force acting on it. In this case, work done by Sun's gravitational force acting on the Earth is zero. Other examples: when a stone is tied to a string and whirled in a circular path, the work done by the tension force in the string is zero. In case of natural satellite like Moon or artificial satellite moving around the Earth, the work done by the Earth's gravitational force is zero. Hence, the work done by the force is said to be zero when the displacement is perpendicular to the direction of the applied force, or if the applied force does not produce any displacement.
Having learnt what is positive and negative work, let us perform an activity and identify the work done. Activity: lift a bag of 3 kg kept on the ground. The force exerted by you on the bag is the work done. Thus, the bag is lifted upwards. In this case, there are two forces. One is the force that you exert on the bag, and the other is the force of gravity that acts on the bag. Can you tell which force does the positive work? Well, the force applied by you on the bag does the positive work, since it acts in the direction of displacement of the bag, whereas the gravitational force of the Earth does negative work as it acts opposite to the direction of displacement. Thus, we can conclude that the work done is negative when force acts opposite to the direction of displacement, whereas the work done is said to be positive when the force acts in the direction of displacement. Let us solve some problems based on work.
1. A man pushes a book by applying a force of 6 Newton. Find the work done by this force as the book is displaced through 30 centimeters along the direction of the push. Solution. Let us first write the given data in proper units. Given force F is equal to 6 Newton. Displacement S is equal to 30 centimeter or 0.3 meter. Formula: W is equal to F into S. Let us substitute the given quantities in the above equation. W is equal to 6 Newton into 0.3 meter, which is equal to 1.8 Newton meter, or W is equal to 1.8 joule. 2. A body of 0.5 kilogram thrown upwards reaches a maximum height of 5 meter. Calculate the work done by the force of gravity during this vertical displacement. Solution. Let us first write the given data in proper units. Given mass m equal to 0.5 kg. Displacement s is equal to 5 meter. Acceleration due to gravity is equal to 9.8 meter per second square. Formula. The force due to gravity is given by F is equal to mg is equal to 0.5 into minus 9.8 is equal to minus 4.9 Newton. Here, negative sign is introduced as the acceleration is in downward direction, that is, in negative y direction. Now, the work done is given by W is equal to F into S is equal to minus 4.9 Newton into 5 meter, which is equal to minus 24.5 joule.
While defining work, displacement is considered either in the direction of the force or in the direction opposite to the direction of the force. However, it is not always so. In some cases, the body moves at some angle to the direction of the applied force. Let us consider an example of a child pulling a toy with a string attached to it. The force is applied along the string and the toy displaces in the horizontal direction on the ground. In this case, the whole of force F is not utilized in moving the toy, but only a part of it, that is, its horizontal component is utilized. It is this effective force that is responsible for the displacement of the toy. Let us derive a formula for the work done in such case. Let OX be the displacement of the toy by the force F applied in the direction of the string OA, making an angle theta with the direction of motion of the toy. The horizontal component of force is F1. Thus, the work done in pulling the toy is equal to the product of horizontal component of the force in the direction of the displacement and the distance through which it moved. That is, W is equal to F1 into S. Equation 1. We can see that the horizontal component of force F1 is equal to F cos theta. Substituting equation 2 in 1, we get W is equal to F cos theta into S, or W is equal to F into S cos theta. This is the work done by a force acting obliquely on an object. Note that as the magnitude of angle theta changes, the magnitude of effective component of force F1 also changes. Let us see the work done when force acts at different angles to the direction of motion of an object. Case 1. When theta is equal to 0. Substituting theta is equal to 0 in equation F1 is equal to F cos theta, we get F1 is equal to F of cos 0. Since cos 0 is equal to 1, therefore F1 is equal to F. Substituting in equation W is equal to F1 into S, we get W is equal to F into S. That is, when theta is equal to 0, applied force F is equal to the effective force, and so the work done is maximum. In practical life, engine in a vehicle is arranged in such a way that the force produced by it is always along the direction of displacement, so we get maximum work done. Case 2. When the angle theta between direction of force applied and direction of displacement is such that theta is less than 90 degrees but greater than 0, then F1 is less than F. In such case, only a part of the total force applied becomes effective force, and so the work W in this case is less than maximum work W max. Therefore, W less than W max for 0 less than theta less than 90 degrees. We have seen people pulling or pushing a heavy vehicle. Have you noticed that the displacement of the vehicle is along horizontal direction, but the direction of force applied makes an angle theta with the horizontal surface such that theta is less than 90 degrees. Case 3. When theta is equal to 90 degrees. Substituting theta is equal to 90 degrees in equation F1 is equal to F cos theta, we get F1 is equal to F into cos 90 degrees. Since cos 90 is equal to 0, therefore F1 is equal to 0. Substituting in equation W is equal to F1 into S, we get W is equal to 0. Hence, the work done is equal to 0. This means that if the displacement of the body is perpendicular, that is at 90 degrees to the direction of force, no work is done. Note that work becomes 0 under the effect of given force F, but other forces that keep the body in motion are present. For example, in case of a body moving in a circular path, the direction of centripetal force and the direction of displacement at any point which is along the tangential direction are perpendicular to each other. So, under the effect of centripetal force, work done is 0. Case 4. When theta is equal to 180 degrees. Substituting theta is equal to 180 degrees in equation F1 is equal to F cos theta, we get F1 is equal to cos 180 degrees. Since cos 180 degrees is equal to minus 1, therefore F1 is equal to minus of F. Substituting in equation W is equal to F1 into S, we get W is equal to minus of Fs. This means if direction of the force applied and direction of displacement are opposite to each other, then magnitude of work is negative. When the driver of vehicle in motion applies brakes, then frictional force produced due to this is in the opposite direction to the direction of displacement. So the vehicle does work against the frictional force.
Energy. The word energy is very often used in our daily life. For example, after doing some hard physical work, we feel exhausted and we say we don't have enough energy for further work. We regain energy when we consume food. An electric fan does not operate if there is no electricity supplied to it. The motorcycle does not start if there is no petrol in it. Hence, to get work done, we use energy in the form of food, electricity, or fuel. Sun is the main source of energy for activities on Earth. Many of our energy sources are derived from the sun. Concept of energy. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. A raised hammer falls on a nail placed on a piece of wood. It drives the nail into the wood. winding a toy spring makes the toy moving. Water flowing from great heights can cause turbines to move. An arrow released from the stretch bow can travel a long distance. In all these examples, objects acquire the capability of doing work. An object having a capability to do work is said to possess energy. When an object does work, it loses energy. When you throw a cricket ball, you do work and lose some energy, and the ball gains energy. When the ball hits the wicket, it does some work in uprooting the wicket and loses energy, and loses the ability to do any further work. Here, the ball in motion has capacity to do work, and it is said to possess energy. Similarly, falling hammer, twisted spring, flowing water, and stretched bow have capacity to do work, and hence they possess energy in them. Hence, energy is defined as the capacity to do work. Energy requires only magnitude for its complete description. Direction is not necessary. Hence, energy is a scalar quantity. Unit of energy. Energy possessed by a body is measured in terms of its capacity of doing work. Hence, the units of energy and work are the same, that is, joules in MKS or SI and ergs in CGS system. Forms of energy. Energy exists in different forms, such as mechanical energy, heat energy, chemical energy, electrical energy, light energy, and atomic energy. Can you identify the forms of energy involved in following examples? Energy in a moving body. Mechanical energy. Burning coal. Heat energy. Lightning during thunderstorms. Light energy. Dry cells used in batteries. Chemical energy. Working of motors. Electrical energy. Atomic reactors. Atomic energy. Let us focus on mechanical energy. It can be further categorized in two types. 1. Kinetic energy, and 2. Potential energy. Let us see the types of mechanical energy one by one. Kinetic energy.
Let us perform some activities to study energy possessed by a moving object.
Take two identical balls, say A and B. Place the ball B at a point. Roll the ball A with some velocity towards the ball B, and what do you observe? When the ball A hits the ball B, the ball A comes to rest, and the ball B starts rolling and travels some distance before coming to rest. Here, the ball B does some work against the frictional force. Now, give little more velocity to ball A and roll it towards ball B. Now what do you observe? The ball B rolls faster and travels a longer distance before coming to rest. Hence, more work is done by ball B in this case. From this activity, we observed that faster balls has more energy than the slower ones.
Activity. Take a metallic sphere, say of 250 grams. Take a tray with a 10 centimeter thick layer of moist soil in it. Now, take the sphere and raise it to a height of 25 centimeters from soil tray. Now, allow it to fall freely. What do you observe? The metal sphere creates a depression on the sand bed. Now, allow the sphere to fall freely from a height of 50 centimeters, then 100 centimeters, and finally 150 centimeters, such that all the depressions are distinctly visible. Observe all the depressions. What do you notice? You will notice that depressions of different depths are created. The sphere is under the effect of force in each case, and so when it is dropped from some height, it does work on the layer of moist soil. Due to this, a depression is formed on the sand bed. As the distance travelled by the sphere increases, the work done by the sphere also increases. As a result, the depth of the depression also increases. Hence, an object moving faster can do more work as compared to an identical object moving relatively slow.
Now look at these examples. The bullet fired from the gun, a flowing water, a blowing wind. All these objects in motion are capable of doing work, hence they possess energy. The energy possessed by an body by virtue of its motion is called kinetic energy of the body. The kinetic energy of a body moving with certain velocity is equal to the work done on it to make it acquire that velocity. Now, let us find an expression for the kinetic energy of a moving body in terms of its mass and velocity. Expression for kinetic energy. The kinetic energy Ek of a body of mass m moving with a velocity v can be measured by calculating the amount of work done w by force F required to set that body into motion from its state of rest. Consider a body of mass m moving with velocity u. This is its initial velocity. Now let a force F be applied to the body as body displaces through a distance s, so that its velocity changes to v. This is its final velocity. Let a be the acceleration produced in the body. The work done w by the force is given by the product of force F and displacement s. W is equal to F into s, 1. From the equation of motion, we have v square is equal to u square plus 2as, or v square minus u square is equal to 2as, or s is equal to v square minus u square upon 2a. 2. Now the force F brings out an acceleration of a in a body of mass m. Then we have F is equal to ma. 3. Substituting the equation 2, and 3 in equation 1, W is equal to m into a into b square minus u square upon 2a. W is equal to 1 upon 2m b square minus u square. W is equal to 1 upon 2 mv square minus 1 upon 2 mu square.
4.
Let the body be at rest initially. Therefore, initial velocity u is equal to 0. Hence, W is equal to 1 upon 2 mv square. The kinetic energy of a body is equal to work done by force to set that body into motion. Hence, the mathematical expression for kinetic energy
Ek
is equal to 1 upon 2 mv square.
In case of an object in motion, the work done on the object is given by equation 4. W is equal to half mv square minus half mu square, which is nothing but the change in the kinetic energy.
Let us study some numerical examples. 1. Find the kinetic energy of a ball of mass 500 grams moving with a speed of 20 meters per second. Solution. Let us first write the given data. Given mass of the ball m is equal to 500 gram is equal to 0.5 kg. Velocity of the ball b is equal to 20 meter per second. Formula.
Ek
Is equal to 1 upon 2 mv square.
Ek
Is equal to 1 upon 2 into 0.5 into 20 square.
Ek
Is equal to 100 joule. 2. If the velocity of the body becomes 2 times its initial velocity, then by how many times its kinetic energy will increase? Solution. If m and u are the mass and the initial velocity of the body, then its initial kinetic energy is given by I
Ek
is equal to 1 upon 2 mu square. Now if the velocity increases and the final velocity is v, which is twice of the initial velocity u, that is v is equal to 2u. Then the final kinetic energy is F
Ek
is equal to 1 upon 2 mv square. Substituting v is equal to 2u. F
Ek
is equal to 1 upon 2 m on the whole 2u square. F
Ek
is equal to 4 into 1 upon 2 mu square. Substituting I
Ek
for 1 upon 2 mu square. F
Ek
is equal to 4 into I.
Ek
Hence, the final kinetic energy is 4 times the initial kinetic energy when the velocity of the body becomes 2 times its initial velocity.
3. Calculate the work to be done by a scooterist to increase his speed from 5 meter per second to 10 meter per second on a level road if the mass of the scooter and the scooterist is 150 kg. Solution. Let us first write down the given data. Given mass of the scooter and the scooterist m is equal to 150 kg. Initial velocity u is equal to 5 meter per second. Final velocity v is equal to 10 meter per second. Let us calculate the initial kinetic energy of the scooter, which is given by the formula EIK is equal to half m into u square. Substituting the values in the given equation, we get the initial kinetic energy EIK is equal to half into 150 kg into 5 square, which is equal to 75 into 25, equals to 1875. Therefore, the initial kinetic energy EIK is equal to 1875 joules. The final kinetic energy of the scooter is given by the formula EFK is equal to half m into v square. Substituting the values in the given equation, we get the final kinetic energy EFK is equal to half into 150 kg into 10 square, which is equal to 75 into 100, equals to 7500. Therefore, the final kinetic energy EFK is equal to 7500 joules. The work done is equal to the change in the kinetic energy, which is equal to final kinetic energy EFK minus initial kinetic energy EIK. Substituting the values from equation 1 and 2 in equation 3, we get W is equal to 7500 minus 1875 equal to 5625 joules. Thus, the work done by the scooterist is 5625 joules.
Potential energy. Let us look at the following facts. Water cannot go from a well to an overhead tank on its own. You need to use a machine for it. But water can come from overhead tank to the ground level tap on its own. Is it possible to release an arrow without pulling the string of the bow? No. We spend energy to pull the string of the bow. A child's toy moves when its key is rotated. From where does it get its energy to move? It is the energy stored in it, in the twisted spring. A stretched spring can do work whereas the normal spring cannot do the work. Thus, water raised to some height, stretched bow, and twisted spring have energy stored in them because of their position or change in shape. This energy is called potential energy. Thus, potential energy is defined as the energy possessed by a body due to its position or configuration.
Potential energy of an object at a height. When an object is raised through a height, its energy increases. This is because work is done on it against gravitational force while moving it. The energy present in such an object is the gravitational potential energy. It is defined as the work done in moving an object from the ground to some point against gravity. Let us derive the expression for potential energy of an object at some height.
Expression for potential energy. Consider an object of mass m is raised to height h above the ground level. There is a gravitational force acting on the object in the downward direction. The magnitude of gravitational force is given as F is equal to m into g, mass into acceleration due to gravity. 1. Work done in lifting the object to a height h against the gravitational force is given by W is equal to F into S. Here, S is equal to h. Therefore, W is equal to F into h. From 1 and 2, we obtain the work performed as W is equal to M into G into H, which is equal to mgh. This work is done on the object in raising it to height h. This is the potential energy of the object at that height. Therefore, PE is equal to mgh.
Another symbol for potential energy is EP, where E stands for energy and suffix P for potential energy. Note that the potential energy of an object at a height depends on the zero level or the ground level that we choose. That is, an object can have certain value of potential energy with respect to one level and a different value of potential energy with respect to another level. Also, the work done does not depend on the path along which the object is moved. For example, consider a block is moved to a height h from position A to position B along two different paths. In both the cases, the work done W is equal to mgh. This is because work done depends on the initial and final position of the object and not the path along which it is raised. Let us now solve some numerical
Example 1. Calculate the potential energy acquired by a 10 kg hammer when it is raised to a height of 10 meters. Solution. Let us first write the given data. Given mass of the hammer M is equal to 10 kg. Height h is equal to 10 meter. Acceleration due to gravity g is equal to 9.8 meter per second square. Formula. PE is equal to mgh. PE is equal to 10 into 9.8 into 10 is equal to 980 joule. Hence, potential energy acquired by the 10 kg hammer when it is raised to a height of 10 meter is 980 joule. Law of conservation of energy. In addition to mechanical energy, we come across many forms of energy. Heat energy. We use heat energy to cook our food. Heat energy is obtained by burning wood or biogas or LPG, that is, liquefied petroleum gas. Electrical energy. Electrical energy is used for operating electric motors and lighting our homes. It is produced using generators or batteries. Solar energy. Sun radiates energy in the form of heat, light, and other radiations. This is the main source for the activities on Earth. Plants use this energy to prepare food by photosynthesis. Chemical energy. This is the energy liberated as a result of chemical reaction. The chemical energy stored in dynamites is used for explosions in mines. Nuclear energy. when some unstable atoms break up, that is, undergo fission, or light elements combine, that is, undergo fusion, they release tremendous amounts of energy. This energy is used to generate electricity. All these energies can be converted from one form to another form. For example, let us consider the energy conversions in hydroelectric power station. Energy conversions in hydroelectric power station. At a hydroelectric power station, water is stored at a greater height. This water possesses potential energy. The water is allowed to flow under gravity to a lower level through large pipes. In this process, the potential energy of water is converted into kinetic energy. This kinetic energy of the water is used to rotate large turbines, which in turn activates the electric generator, and electrical energy is generated. Kinetic energy of water is converted into electrical energy. Hence, energy obtained in one form is the outcome of conversion of energy from various other forms. Similarly, solar energy is converted to chemical energy by plants, and wind energy, tidal energy get converted into electrical energy. The following figure will give an idea about how different types of energies get converted or produced from electrical energy. The law of conservation of energy states, energy can neither be created nor be destroyed. It can be converted from one form to another. The total amount of energy in the universe always remains constant. Hence, one form of energy can be converted into another form and vice versa. One cannot generate it, nor can one destroy it. Suppose we consider a hot cup of tea placed in a closed room. This is referred as a system. As tea cools, it loses energy, but the air in the room gains equivalent energy. Hence, energy of an isolated system remains constant. Let us understand this by considering the example of a simple pendulum. Simple pendulum. A simple pendulum consists of a small metal ball called bob suspended by a long thread from a rigid support. The bob is free to swing back and forth when displaced. Initially, pendulum is at rest with its bob at the center or the mean position O. After that, the pendulum bob is pulled aside to position P and released, such as the bob starts swinging between positions P and Q. The bob of the pendulum comes at an instantaneous halt before starting its journey in reverse direction at extreme points P and Q. The velocities of the bob at P and Q are zero. Hence the kinetic energy is zero. Here, the bob is at some height compared to its mean position and hence possesses potential energy. As the pendulum bob swings from extreme positions to the mean position, the potential energy decreases and kinetic energy increases. The bob, while passing through the mean position, has no potential energy, but possesses the only kinetic energy. At any intermediate point, the energy of the bob is partially potential and partially kinetic. Yet at all times, the sum of the potential and kinetic energies of the bob remains constant. There is no loss or gain of mechanical energy, only a transformation from kinetic energy to potential energy and vice versa. This explains the conservation of energy.
Thus, the sum of the kinetic energy and the potential energy of an object would be same at all points and is equal to its total mechanical energy. Let us derive a mathematical expression to prove that the total energy of a system remains constant.
Let a body of mass m fall freely from a height h above the ground. Let us calculate its kinetic and potential energy at three different positions. A. At height h above the ground level. B. When the body has fallen a distance x. C. On the ground. 1. At position A. The body is falling freely from point A. Hence its initial velocity at A is 0. Therefore, kinetic energy is equal to 1 upon 2 mv square, which is equal to 0. The point A is at a height h above the ground. Therefore, potential energy is equal to mgh. Total energy is equal to kinetic energy plus potential energy, which is equal to 0 plus mgh. Therefore, total energy is equal to mgh. 2. At position B. As body falls under gravity, it gets accelerated in downward direction. Let the velocity of the body at point B after falling a distance x be v1. The displacement s of the body is s is equal to x. Initial velocity u is equal to 0. Using the equation of motion, v square is equal to u square plus 2gs, where g is equal to acceleration due to gravity. Hence, v1 square is equal to 2gx. U is equal to 0. Therefore, kinetic energy at B is equal to 1 upon 2 mv1 square is equal to 1 upon 2 m on the whole 2gx. Kinetic energy is equal to mgx. Now let's calculate the potential energy of the body at B. At position B, the height of the object above the ground level is equal to h minus x. Potential energy is equal to mg into, on the whole, h minus x. Potential energy is equal to mgh minus mgx. Now total energy of the body at B is, total energy is equal to kinetic energy plus potential energy. Total energy is equal to mgx plus mgh minus mgx is equal to mgh. 3. At position C, let v be the velocity acquired by the body on reaching ground. Initial velocity u is equal to 0. Displacement s is equal to h. v square is equal to u square plus 2gs. v square is equal to 2gh. Ke is equal to 1 upon 2 mv square is equal to 1 upon 2 m into, on the whole, 2gh. Ke is equal to mgh. At position C, that is, at the ground level, h is equal to 0. Pe is equal to mgh is equal to 0. Total energy is equal to kinetic energy plus potential energy is equal to mgh plus 0, which is equal to mgh. From statements 1, 2 and 3, the total energy of the system remains constant at the three different positions A, B and C respectively. Hence the total energy, that is, the sum of kinetic energy and potential energy, always remains constant at each point of motion.
Rate of doing work.
In day-to-day life, one having large physical strength is said to have more power. But in science, the term power is used for engine, pumps and motors, etc. To understand the term power, we shall consider a few examples. A man takes 5 minutes to go up a staircase. A boy goes up in the same staircase in 3 minutes. The work done by both is same, but the time required is different. A tank which is on top of a building is to be filled with water. If it is filled with a bucket, it may require a day to do so. A water pump, on the other hand, can do this work in just a few minutes. The work done is the same, but the time required is different. Deepak, Rahul and Ketan planned to visit a hilltop temple. Deepak went walking, Rahul went cycling, Ketan went by a car, all taking the same route. It is but obvious that Ketan will reach first, then Rahul, and lastly Deepak. Work done in all the cases is the same, but the time required by each one of them is different. That the power measures the speed of work done, that is, how fast or how slow the work is being done. Power is defined as the rate of doing work. Expression of power. If W is the work done in time t, then power P is given by power equals work upon time. P is equal to W upon T. Unit of power. The unit of power is watt. When 1 joule of work is done in 1 second, the power spent is said to be 1 watt. P is equal to W upon T equal to Newton meter upon seconds equal to joule upon S equal to watt. The unit of power watt is named after a Scottish inventor, James Watt. Watt is a small unit of power. Sometimes bigger units like kilowatt are used. 1 kilowatt is equal to 1000 watts. Power is also measured in a unit called as horsepower, HP. This unit is used in the industry. 1 horsepower is equal to 746 watt.
Commercial unit of energy.
The energy consumed in households, industries, and commercial establishments are expressed in kilowatt hour. 1 kilowatt hour or 1 kWh is equal to 1 kW into 1 hour equal to 1000 watts into 3600 seconds is equal to 36 into 10 raised to 5 joule is equal to 3.6 into 10 raised by 6 joule. Hence the energy consumed in 1 hour by an appliance of 1 kW is 3.6 into 10 raised to 6 joule. In simple terms, 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. In an electricity bill, electric energy used during a month is expressed in terms of units. Here, 1 unit means 1 kilowatt hour. The 60 watts bulbs that you use in your table lamp simply means the bulb consumes electrical energy at the rate of 60 joule per second. The unit called horsepower originated long back when steam engines first replaced horses as a source of power. 1 horsepower or 1 HP is equal to 746 watts. W. Kilowatt hour is the unit of work done or energy consumed.
Numerical
Example 1. A person carrying a bag of total mass of 25 kgs climbs up to a height of 5 meters in 30 seconds. Calculate the power delivered by him to the bag. Solution. Let us write the given data. Mass of the bag, m, is equal to 25 kilograms. Height, h, is equal to 5 meters. Time, t, is equal to 30 seconds. The power delivered to the bag is equal to the rate of work done on it. That is, P is equal to W upon T. The work done is given by the product of the force and the displacement. That is, W is equal to F into S. The force acting on the bag is given by F is equal to M into G. Hence, 1. The force exerted is equal to the weight of the bag. F is equal to M into G is equal to 25 into 9.8 is equal to 245 N. 2. The work done by this force is taking the bag up by 5 meter is W is equal to F into S is equal to 245 into 5 from 1 is equal to 1225 joule. 3. The work is done in 30 seconds. Hence, power delivered P is equal to W upon T is equal to 1225 upon 30 from 2. P is equal to 40.83 watts. 2. An electric bulb of 60 watt is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. Solution. Let us first write the given data in proper units. Given power of the electric bulb P is equal to 60 watt equal to 0.06 kilowatt. Time used T is equal to 6 hours. We want to find out units of energy consumed. formula to be used is energy consumed is equal to power in kilowatts into time taken in hours, equal to 0.06 into 6 is equal to 0.36 kilowatt hour is equal to 0.36 units. 3. An electric bulb of 25 watt is used for 10 hours per day. Calculate the units of energy consumed in 10 days by the bulb. Solution. Let us first write the given data in proper units. Power of electric bulb is equal to 25 watt is equal to 0.025 kilowatt. Time for which bulb is used is equal to 10 hours per day. Therefore, the total time the bulb is used is equal to 10 into 10 is equal to 100 hours. Formula. Energy consumed is equal to power in kilowatts into time taken in hours. Solution. Energy consumed is equal to 0.025 into 100 is equal to 2.5 kilowatt hour is equal to 2.5 units.